It's going. Hello, welcome to Extragalactic Astronomy for this semester. I'm David Collins. I'll be your professor for the duration. So I'm going to get into it and talk about what to expect this semester. So I'm going to go through. I didn't. Anyway. So I'm going to go through the syllabus, which covers what to expect this semester, and then I'm going to go through kind of a brief history of human knowledge of extragalactic objects, starting from what you can just see with your naked eye up through a couple of weeks ago when JWST, actually there's no JWST in there because I haven't gotten there yet because that data is all super fresh. So, okay, so this is extragalactic astronomy, astrophysics. I can't remember what the title actually is. I just call it Exgal. So I am David Collins. Office hours, usually I do office hours the day before something is due or the day before a test, usually at the end of the day. If as the need for office hours arises, I'll talk to you guys about what actually works. So usually those are on demand kind of right before something is due. If you want other times, emailing me is best and making sure that I'm available. I lack social skills while I'm trying to program, so if you catch me when I'm trying to code, my ability to interact with human beings is down around 0. So it takes a minute for that to turn back on. So if you email me first, that's better. I try to be polite, but I might stare at you blankly for 5 minutes while I try to understand where your semicolon is supposed to go, and then realizing that you're not code. I'm a little slow sometimes. All right, so hopefully everybody's taken Intro to Astro last semester or the previous year or something equivalent, so I need everybody to have that basic background. However, I'm going to assume that it went about as well as I think it did. So I'm going to cover all the background. I'm going to cover everything that I need you to know. So we'll go over that thing. Also, I really believe that you don't ever learn anything one time. So everything I need you to know, I'm going to go over again. Even though I expect that you've seen a lot of this already. So that includes Calc 1 and 2 and 3 and Physics 1 and 2. And more importantly, I'm interested in very large objects. Okay, so the book is Schneider's Extragalactic Astronomy and Cosmology. Get the second edition. There's a huge difference. There's a lot of stuff that's missing from the first edition. It came out like a year and a half later. So I started teaching out of this book shortly after it came out, and I'm like, why are you not talking about X, Y, and Z? And there's a lot of things that he's missing. And then the next, 2 years later, the next edition came out, and he talked about all the things that I liked. It's great. Get the second edition. Don't get the first edition. Make sure you don't have the first edition because it's going to throw you off. It's easier to find digital copies of the first edition. So if that's all that you can find and all that you can afford, let me know. But try to get the second edition. It invariably, somebody turns in a reading that's from totally the wrong chapter. And I'm like, yeah, I'm not covering microlensing this year. But now you read about it, so that's cool. It's always the microlensing section. So, okay, other books. I just put this up here for mostly to be clear about where I'm drawing from, but also to point you guys to other books that you might find interesting as your studies go on. So we're going to be drawing mostly from Schneider, but Long-Air's Formation of Galaxies is a really key book. It's really great. It's an advanced level text, so you don't read it now, read it when you're done with this class. Binney and Merrifield is another great one on galactic astronomy. Spark and Gallagher is, it's a really nicely written book. This is one you can just kind of read like a novel. It's really well written. It's pretty intro level. Carolyn Osley, I think you guys use Carolyn Osley for intro, I think. Probably other books and probably other articles, but mostly I stick to the book. Yeah, except for the spots where I don't. Anyway. So okay, what's in the grade? In the grade is a reading, so there's going to be regular readings. There's a lot of reading in this class. Don't take it too seriously, because there's a lot of it. And if you're not a fast reader, I'm not a fast reader. I'll talk more about it, but the readings are just to prime you for when I talk. So participation, that means show up and be awake enough. So I don't have any really strong constraints on what participation counts. So just show up, ask questions, be engaged. It's pretty straightforward. This is fun stuff. Homework. I should put the percentages up here. So reading and participation are both 5%. Homework is, I think, 30-something%. And there's two kinds of homework assignments. There'll be paper homework assignments where you do it, where you solve problems like most other courses. And then there are a series of Jupyter notebooks, which are code-based homework assignments. And the reason I do this is for a couple of reasons. One, code is vital. Learning how to program is essential. If you're going to be successful as a physicist, you have to know how to code. So I'll teach you some Python. And if you've seen some Python already, great. And if not, here we will learn some Python. I'll talk more about that in a minute. And then there's a midterm and a final. The midterm will be mid-semester, and the final will be the Monday of finals week. I don't put the final. I always screw it up if I put when the final is in the syllabus, because then I forget and use last year's. So look it up, and it's online. I think it's the Monday at 10. Okay, everything's always due midnight the night before class, so that way I can start the day. I start preparing for class. I grade your homeworks, and then we talk about it. So. That being said, I don't actually start looking at them until like 9 o'clock. So I put the deadline sometime the day before, and then I look at them in the morning. If you turn it in at 2 o'clock in the morning, I don't really care. But practice good sleep hygiene. So don't kill yourself over it. Okay, reading and participation. So reading summaries will be due at midnight, and there's basically 3 parts. First, briefly summarize what you read, and whatever that means for you. If you're a detailed note taker, just take a screen cap or a cell phone picture of your notes and turn those in. That's cool. If you're not a detailed note taker, then just write down a topic from each one of the sections or something like that. Low key, easy stuff. Don't kill yourself, because if you want to try to read everything carefully, you will do nothing but this course. So it's not super bad. I'm just want to set everybody's expectations for the readings. Ask any questions that you have. And this is really why I do the readings this way, because this is a vehicle for you to have the book in front of you and to jot down questions that you have that you don't get, things that are missing, things that you don't understand, terms that he uses, concepts that you want to go over in class, anything that you didn't like, you want to see more. Ask those questions in the reading. If you could make sure that they're separate from everything else. I don't read your reading summary super carefully. If you could separate out your questions so that I can see them, highlight them is fine. Ask questions. This is really the important bit, because this turns the course into a dialogue where we're talking about stuff instead of me just up here monologuing, which I'm perfectly happy to do, but isn't nearly as useful pedagogically. And then the last thing is, how long did this take you? And I ask you this on everything. And I do this for 2 reasons. One, it gives me a gauge of how you're doing, but more importantly, it gives me a gauge of how I'm doing. If I'm assigning homework assignments that take everybody 6 hours to do, then I at least know that I have to give you enough time for that. I'm not judging you at all on how long it takes you. It doesn't impact your grade. It's just a way for me to diagnose how things are going. So I want to have some feedback on how the assignment went. So. Participation, I will randomly point at people and make you talk. So show up. That's really all that's in there. But participation is important, because for A, I talk about stuff that's not in the book. Because since the book came out, we've discovered gravitational waves. JWST was launched. We've imaged black holes. There have been incredible advances in the last 2 or 3 years since the book came out. So this field is constantly having massive overhauls, and I'm going to have to, once we understand the JWST data a little better, I'm going to have to overhaul everything again. So there's a lot of new stuff. So coming to class and showing up is important. More importantly, I will talk faster and faster and faster as I go if you don't slow me down. So as soon as I lose you, stop me, because otherwise I'll just keep going. And I can cover an enormous amount of material that you won't understand. So stop me and ask questions. And and answer my questions when I ask. I will ask a lot of kind of group questions. You can just holler. Homework is 30% of your grade, roughly every other week. To turn them in, just take a cell phone. So for the paper homeworks, just take a cell phone picture of your work and turn it into Canvas. That works pretty well, and everybody seems to figure out how to light your homework properly, so I really don't have any problems with that. Late assignments, if I get it after I start grading it, then I'll take off 10%, and after I talk about it in class, I'll take off 50%, but that's good for the rest of the semester. Turn your homework in. I want you to do it more than I want to take points off. So yeah, I'll go over everything. And again, one of the problems is going to be how long did each of these problems take you? Because I'm constantly tweaking the homeworks and making new problems, and sometimes my ideas are really funny and take forever. Sometimes they're not. So it's a useful diagnostic for me. The Python homeworks, there are 7, I think, Python exercises. And these are short notebooks to get you familiar with Python and programming if you haven't already. I'm assuming that nobody has any programming experience. That's my base level, is that nobody knows anything, and we'll build up from there. So how many of you have some Python experience? A little bit, a couple of you. How many of you have 0 coding experience at all? A couple of you, okay. So we will, don't worry, it's all pretty straightforward. I really slow pitch everything, so it'll be all right. That being said, there's a homework due tomorrow. Install Anaconda so that we can actually do it. Let's see. Yeah, grades are based on effort, not outcome. So if you try and you can't get it, that's fine. I want to see that you tried something, and that's really the important bit. So this is an effort more than success. Put your hands on it, beat your head against it for a little bit. But if programming gives you a panic attack, just try it twice and then turn in what you did. So I'm not looking to make anything painful here. That being said, the homework exercises are really about getting color from temperature. So there's useful outcomes there. Okay, everything's posted on YouTube. Not everything. Sometimes I flake. Sometimes I forget to hit record. Sometimes my laptop fills up and the recording is lost. So all kinds of things happen with the recording. So most of them get up there, but it's not a substitute for coming to class because sometimes I flake on the recording. But it's there in case you need it for this, especially for the topics get more challenging. Midterm is 25%, mid-March. The final is 35%. It's the Monday at 10 o'clock. It covers everything. Final is mostly the second half. But let's see, I might make the graduate version more difficult. I think there's only one grad student in this semester. I let everybody have one 8.5 by 11 inch sheet of paper, both sides, just that one sheet of paper, with whatever you can cram in it. Because this could turn into a memorization class really fast, and that's not really what I want. So there's a lot of facts to know, so that's what that's for. Okay, reading's 5%, discussion is 5%, homework is 30%, midterm is 25%. Grading rubric looks like this. Okay, so what are we going to cover? Does anybody have any questions about homeworks or code homeworks or anything? Readings? Plenty of space to ask them later. Okay, so mostly this class is about galaxies. So we're going to talk about what does a galaxy look like? What are the physical properties of galaxies? What is their density distribution? What's the velocity distribution? What's a distribution? What does a galaxy look like? And we'll talk about the physics of the galaxies. What's actually in the galaxy? How does it work? What's going on? How does the kinematics work? We'll talk about groups and clusters of galaxies. So this is how galaxies party. And we'll talk about the formation of galaxies, where they come from. And this one, I'm going to tell you now, I'm going to tell you a story that actually might be wrong. But I'm going to tell you the story anyways, because as of October, it was right. But then the data came out and everybody's like, well, what the hell is that? we'll talk more about that. It's gonna be super fun. I actually don't know how bad it is, so maybe we're fine, maybe we're not. It's exciting stuff. So that's what doing research science is about, right? Is not knowing what the hell is going on for a long time. We talk a lot about dark matter. So how we know that there is dark matter, I just made a big assumption that there is dark matter. So what's the problem? So dark matter is a problem, not a solution. Or, yeah, let's put it that way. What is the problem? Why do we need dark matter? And why do we think that dark matter is the solution to that problem instead of something else? We talk about star formation because we have to, because star formation and galaxy evolution are intimately tied together. And stars are really the way we learn basically everything. Here's another fun thing. When I first started teaching this class, I said the only way we get information are photons and neutrinos, but now we have gravitational waves too. The gravitational observatory is open since I started teaching this class. But still, even until we have 1,000 of those, stars are going to be how we learn everything about galaxies. So we'll talk about star formation, birth, and death. And we'll talk a lot about black holes. Not the general relativity of black holes. That really only matters when you're really close to the surface, and there are exactly 2 pictures of that, which there weren't before when I started teaching this. The Event Horizon Telescope has some really magnificent pictures of black holes. So we'll talk about how we know they're there and what they do. I'm not going to spend too much time on black hole formation or the details, because you need general relativity, and nobody here has general relativity yet, and that's okay. And then we'll talk about cosmology. Again, the cosmology bits that don't need general relativity, which is a fair fraction, so we can cover a lot of cosmology. Okay, so this is the tentative plan for what we're going to do. So we'll talk about stars and color first, and then distance and the galaxy structure. So you guys talked about the distance ladder in intro, right? A little bit. We'll spend some more time on that because now we've got all of these galaxies defined. We'll talk about galactic structure. We'll talk about our motion in the galaxy, and the reason that we do that is so that we know what our galaxy is doing, because we compare then to other galaxies, and we look at the motion of other galaxies. But it turns out it's easy to measure the rotation of a distant galaxy, but it's really hard to measure the galaxy that we're sitting in, because we're in it. We'll talk about the virial theorem. Did you guys talk about virial theorem ad nauseum? Like, are you sick of virial theorem yet? Peter loves it. I love it. It's great. It's a very cool thing. We'll talk about virial theorem. We'll derive it, and we'll use it. We're going to use it a buttload in all of these things. So we'll talk about elliptical galaxies, and we'll talk about where you get elliptical galaxies. We'll talk about spiral galaxies. We'll talk about the formation of stars and the evolution. Then we'll talk about black holes. We'll talk first about things that are definitely black holes. And then we'll talk about things that are probably black holes. And if they aren't black holes, then the universe has some really weird presence for us. If it's not a black hole, things are much stranger and worse than we thought. Then we'll spend several lectures on those, because these are the brightest objects in the universe. Then we'll talk about clusters of galaxies. The midterm will happen somewhere in here. I might do it before we get to clusters. Kind of depends on how long I blah. And then there's spring break, and then we'll talk about cosmology, which is the formation of the universe, of the stuff in the universe. No, not the formation of the universe. That one I don't have. I have the evolution of the stuff in the universe after its formation. T=0 is hard. We don't know what happened at the Big Bang, but basically everything after that we're good. And we'll talk about dark matter candidates. What are the possible dark matter candidates? This is a depressing talk, actually, because I used to have a good story, and now I'm telling the same story, but it doesn't actually work anymore. So it makes me sad, because I don't actually know what the right dark matter candidate is anymore. We'll talk about that later. And then, we'll talk about maybe genes stability, which is one of my favorite things to talk about, and maybe some other stuff depending on how fast we get. All right. And then, let's see, I think I have some. Oh, that sign-in sheet. Does anybody got a sheet of paper that I could borrow for the sign-in sheet? Because I forgot to bring it. Yeah. Do you mind?
This one?
Yeah, that'd be great if you don't mind. Do you want to sign it and start it and send it that way? I always forget to actually click that everybody's here. If you all get dropped, I apologize. To date, that's never happened. And then here is the academic honor code. Don't cheat and stuff. Okay. Does anybody have any questions about logistics? There's stuff that's due tomorrow. You'll need the formatter.
I have a question.
Yeah, go.
Are all these lectures going to be posted on Canvas right before?
I can try to put them up before if you're the kind of person who likes to take notes straight on the lecture slides.
Yeah.
Yeah, I can try to post them before. I'm not in a good habit of doing that, so I can promise that I'll screw it up a couple of times, but I can try to put them. I can try to do that. It used to be when I was first doing this class, it was impossible for me to put the slides up before class because I was like still writing them like as I was walking to class. But now they're all pretty set. Okay, so let's talk about looking up at the sky. So this is the Milky Way over somewhere in North Florida. I was living in northern New Mexico right before I moved here, and the sky there is incredible. So on my drive home, especially in the winters when I would leave the office at night, I would often pull over in the middle of the highway in the middle of the damn nowhere to just look at the Milky Way, because how often do you get to see the Milky Way? You got to drive out to the middle of damn nowhere. But I was living up in the mountains, so I had it really good. So I was a little nervous that I would never see the sky again. Right before I got this job, somebody posted this on Reddit, which is really nice. Like this is some along the coast somewhere. I'm not exactly sure where it is, but it's coastal plains. But you can see the Milky Way like beautifully and clear. This thing here is called the Pied Nebula. But what is this? What are these stripes? Why has it got I've got like two big lines.
It's like the dust in front of the light.
Yeah, so I got this stripe. This is dust that's in front of the light. And this whole thing, there's a bunch of light here from the disk of the galaxy. So we live in this galaxy that's like a pancake. We're like a chocolate chip in this pancake. And we're trying to see in it, but there's all kinds of stuff. So you got to look through the whole pancake here. So you can see kind of the maple syrup that you put on the top. And the bottom, I don't know, my plate isn't as symmetric as outer space is. So you can kind of see the stuff on the top and the bottom, but it's really hard to see through the plane. But you can see it. So this is what the galaxy looks like. That's our home. How do we know it's a galaxy? Well, we'll talk about that in a minute. So what was the first object that's outside of our galaxy that you could see? So way back in the day, you could see the Milky Way pretty regularly because there wasn't so much light pollution kind of anywhere. Yeah.
Andromeda?
Yeah, Andromeda is I think the first extragalactic object that you can see. So there are 3 galaxies that you can see with the naked eye. There's Andromeda, which is kind of hard to see. You got to know exactly where you're looking. There's the Large Magellanic Cloud and the Small Magellanic Cloud, but you can only see those from the southern hemisphere. Those are the Large and Small Magellanic Clouds are orbiting the Milky Way, and Andromeda is off at some distance and it's coming at us really fast, and something weird is going to happen in about 100 million years. So the Babylonians first started writing down astronomy in general, so a couple hundred years BC. So this is, staring up at the sky has predated, written knowledge for real. Oh, I heard this. Okay, I'm going to tell this story. I should put it up here because it's good. I just read this a couple of weeks ago. So you're familiar with the Pleiades, the constellation, the 7 sisters? Only 6 stars are visible to the naked eye. But there are many cultures, the Native Americans, Aboriginal Australians. Think about how far away Australia is from everything else. The Aboriginal Australians didn't really have much contact with the Native Americans in the United States. They didn't have much contact with native tribes in Africa, but there are a dozen or so different old historic stories about the Pleiades that say there's 7 sisters and one of them's missing. And she was captured or whatever. Now, why can you only see 6 stars? Well, because 2 of them are in front of each other. So 100,000 years ago, you could see 7 stars. But now you can't. So the thought of this paper was that this is some of the oldest historical human knowledge, that you used to be able to see 7 stars and now you can't, because everybody's got this story. So anyway, ancient history of astronomy is fascinating, and I don't know much about it. So Hipparchus was the first person that really started writing things down. No, not the first person. Al-Sufi started writing things down earlier, but Hipparchus started writing down the planets and the stars, and is probably responsible for the magnitude scale that I will complain about incessantly throughout this class. Ptolemy, we don't actually have anything that Hipparchus wrote. We only have what Ptolemy wrote 300 years later. So he wrote everything that he thought Hipparchus said. Al-Sufi was the first person who actually wrote down and notated that there are extragalactic objects out there. He's the first person to record Andromeda and the Large Magellanic Cloud. You can see both of those from Saudi Arabia. You can't see the Small Magellanic Cloud from Saudi Arabia. It's too low. So anyway, so we've been looking at extragalactic objects for a long time. So there are about 16 objects that you can see with the naked eye. There's the Large Magellanic Cloud and the Small Magellanic Cloud and Andromeda. I just pointed those in the wrong order. This is the large. This is the small. No, this is the large, and this is the small, and this is Andromeda. And the Small Magellanic Cloud would have been seen by the Aboriginal Australians. Here are some naked eye objects. This doesn't show up all that great, but you can see them. So here we have the Small and the Large Magellanic Clouds. This is over the Atacama Desert. This is the Very Large Telescope in the Atacama Desert. And you can see the Pipe Nebula is upside down because you're on the other side of the planet. This is what Andromeda looks like with 8-minute exposure on a standard SLR. I didn't take it. I stole this from Reddit too. But he has this nice, this guy actually had this nice, puts this nice ring around this, which you actually can't see very well. So there's this ring. This is the core of Andromeda, and this is how big it is, but it's really hard to see. Now, if your eyes were 8 feet across, then you would have the collecting area to see it, and it would look like this, which is kind of magnificent. I mean, it's way bigger than the moon, which really the moon isn't very big, but it's much larger than the moon. I really wish I had those giant 8-meter eyes. So what is this object? Depends on how far away it is. If it's in the Earth, then it's a cloud or something. If it's in the galaxy, then it's some kind of nebula. If it's outside of the galaxy, then it's maybe another galaxy. So it's a difficult problem of determining what this object is. So we'll get back to that. So how do you figure out how far away that is? We'll talk about that in a second. Let's talk about the historical greats, Tycho, Kepler, and Newton. Tycho is super important because he wrote down where all the stars are. So he took very detailed notes of where all the stars are and where the planets are. And he discovered nova and supernova because he was just looking at the sky every day. Periodically, stars would show up and then disappear. Sometimes they would show up really damn bright. Here is, let's see, this is one of his drawings. And A is from Cassiopeia, and I can't read that one. But here he's got these stars, but this one here, this is Nova Stella. That means new star. What the hell was that? Well, I'm going to tell you that stars take a long time to form, but they take very little time to explode. They get really bright. So we'll talk about supernova explosions. So this is not the first time. The first time a supernova was discovered was about 400 years earlier than that. Oh, I wonder if I have. Anyway, I don't have a picture of that. Chinese scientists notated supernova at about 1000 AD. I should have a picture of that up here. Kepler took all of Brahe's data and figured out what's going on. So this is kind of how science works. Science has theorists and observers. So you've got experimentalists who go and break stuff and look at how the world works, and you've got theorists who figure out what it's all doing. Now in the modern era, you've got simulators who try to fake it. So he was one of the first theoretical astrophysicists. Then he came up with the planetary orbits. So he figured out that the planetary orbits are elliptical and the sun's at the center, and they almost killed him for it because he didn't say that, I don't know. Galileo then came later and invented a telescope. I don't think he invented it, but he certainly pointed it in the sky. Realized that these are all full of stars. And then he sold telescopes to the military-industrial complex, which is how he supported himself. There's a long history of science being in bed with the military-industrial complex, for better or for worse. So in 1610, he realized that all of this stuff is actually stars. So these are clearly stars, but this white stuff in here is also stars. Newton then came along, started a great rock band, invents calculus, discovers F equals ma, then turns 21. I did not understand calculus when I turned 21. I had taken it, but I didn't really get it. He came up with this fascinating question: what keeps the stars up? The universe is expanding, and a lot of people hate that, but it is. More importantly, it has to be expanding or falling on itself. And I'll show you why later, but it's either expanding or contracting, or it's not infinite. So he had this problem of how do the stars stay up? Asks the question if the universe is really finite, because if it's not finite, gravity's going to win. Immanuel Kant, who was a philosopher, I guess a scientist. Back in the mid-1700s, what a scientist is kind of still being developed. They were still working on what the scientific method was. He realized that rotation could do it. So if you have something that's rotating, it can support itself against gravity. And that's useful for some things, but not for the whole universe. It's useful for galaxies, for planetary systems, for disks and stuff. And he was one of the first people who proposed that these nebula, and I'll tell you what I mean by nebula, may be what he called island universes. So Charles Messier then came a little later and went on a hunt for things that aren't comets. He really wanted to find comets because people believed that comets brought, evil or something. I try to not learn too much about superstition. So people were superstitious about comets, so everybody wanted to find comets and name them after themselves. So he went and looked at all the things that certainly aren't comets. And then we have this great catalog of objects in the sky. Some of them are galaxies. Some of them are just fuzzy things, like the Pleiades is M45 and M31 is Andromeda. So this is in our galaxy and not very far away. This is another galaxy that's pretty far away. But he didn't know that. He had no idea what this was or what this was. I think he probably knew what the Pleiades were. But he didn't have any idea what this was. And is that different from this thing? Is that different from this object or this blurry thing? What are these objects? I took a little bit of time to really start to understand what these things were. So William Herschel took a bunch of readings of measurements of the brightnesses of stars around the sky and said, okay, let's assume that every star is the same brightness intrinsically, and then because the flux that I see is going to be the brightness intrinsically divided by the area of the surface to us. So as you get further away from something, it gets less bright, right? So he was just saying, okay, well, we're just going to map the brightness that I see to the brightness to the distance, which is almost great, except for the fact that the base assumption that every star is the same brightness is totally awful, but it's a great start. So, okay, assume that the stars all have intrinsically some luminosity. The flux that we see is that luminosity divided by the distance squared. This is an equation that I should have this on its own page. This is an equation that underpins like 30% of what we talk about. And it made this map. of the galaxy. So this is where all the stars are in the galaxy that he had. And he's right, it's kind of flat and elongated, but I mean, what's this dip in here? Why do these things look so close? What's this way over here? So here is some stellar dust lanes. I can tell you that now because I understand how stars work. These guys over here look further away because there's dirt in the way and make them look dimmer, which makes them look further away. This is a balancing act that we'll have to deal with. Dirt in the way makes things look dimmer. So if you want to figure out how far away something is, you also have to sort out what the dirt is. So we'll talk about that too. He didn't know that. It took a long time to really get our heads around that. But he did get this nice image or this nice figure of what our galaxy looks like. Oh, I did make it a big page by itself. Look at me, planning ahead. F is the flux that I have at me. This is what I get. And L is the luminosity at the star. And D is the distance. So I have all these photons. I just spread them out. And by the time it gets to me, they've been spread out by this much. So this equation will show up a bunch of times in a bunch of different forms. And it's not going to look like this. We're going to use magnitudes. Yeah.
Do you mind explaining it?
Yeah, totally. Okay, so F is the flux. This is the light that I experience. And I'll put units on this later. Yeah, I'll put units on it later because the units get confusing. So that's the light that I collect with my telescope. The luminosity is the brightness of the object at the object. So that's how many photons per second it's spitting off. This is how many photons per second I'm collecting. And then this is the distance to the object. So let me draw a picture. Was that?
Like the inverse square
Yeah,
law.
this is exactly the same as the inverse square law that you see in all kinds of places. So it's just like the inverse square law in gravity. It's just like the inverse square law in E&M. And it is just geometry. Where's the eraser? Oh, dope, you found it. Okay, here's an object that I was looking for but does not work. Watch. Oh, hey, that worked better than I expected. It does not work well. I have a hatred of whiteboards. I will take being covered with chalk to not have to deal with all of this ghosting. Okay, so actually, let's talk about units for a second. So F is a flux, and this is in, let's say, ergs. Erg is an energy. Okay, I use CGS for everything because I'm an astronomer. And so I use the centimeter second gram system versus the SI system, which is meters, seconds, and kilograms. This one also includes the ampere, where this one does not, and that is why I use this one. I'll explain that later. So there's some weird and complicated reasons why astronomers all use CGS, but we all use CGS. So everything's in centimeters, grams, and seconds. So the energy in CGS is an erg. That's equivalent to a joule. It's like 10 to the 7. It's like 10 to the minus 7 joules. The force is a dyne. That's like a newton. It's like 10 to the minus 4 newtons. An erg, this is equal to a gram centimeter squared per second squared. Okay, it's just a mass times a velocity squared, right? 1/2 mv squared. How big is a gram? Like, is it super heavy or is it super light? It's super light. A gram is like a paper clip. A centimeter is, yay, and a second isn't very long. So a centimeter per second, not very fast. An erg is like an ant doing a push-up. It's about the energy of an ant running around. Very little amount of energy. However, when we're talking about supernova, we need a whole lot of whatever unit you use. So it doesn't matter if I use this tiny little unit. So erg is an energy, and I'll say that again if you need a refresher, because you don't deal with ergs very often. Erg is an energy. So the flux is an ergs per second per area. Because why per area? Because if I double the size of my telescope, I get that thing looks twice as bright, right? Because I get twice as many photons. And I'm going to put a question mark here because there's some other units that might creep up that I don't want to talk about right now. We'll talk about them later. I want to talk about these units. So flux is in energy per second per area. Now, there might be some other things there. Might be a per wavelength in there too, because I might only be looking at one wavelength. Might be a per solid angle because I have to integrate over the how much of the sky I see. We'll talk about that in a second. Ergs per second, that's the power. It's how many photons I'm getting. Per area, that's the size of my collector. Equals the luminosity. The units of the luminosity are just ergs per second. Divided by 4 pi for geometry, distance to the object squared. So the luminosity is in ergs per second. This is how many photons per second the star is spitting out, like total. And that amount of photons, so here I've got a star, like here, a nice green star. There aren't any green stars. So I have L photons per second that are coming off of this star. They all get spread out over the area that they're filling. So if I'm out here, say this is me on the Earth, so if I'm at the Earth, the total number of photons in ergs per second has got to be the flux that I see at this times the area of the surface. Does that make sense? I've got 400 photons coming out of the star. I spread them out over this area. I've got 400 photons divided by my area. It's just a conservation law and geometrical dilution. So it's just geometry. So the area, so flux times 4 pi r squared, where this is r, is going to be the area of this sphere. So the flux times the area of the sphere has got to be the total number of photons that I'm getting out at the beginning. Right? So L is the total number of photons. F is the flux that I'm going to experience. It's really the total number of photons spread out uniformly over this sphere. F is the flux that I experience here. And they're related by F equals L over 4 pi d squared, or r squared, let's call this. D be consistent. Does that make sense? If you want me to go through that again tomorrow, just ask. Because getting our heads around this expression is going to be very most important. This expression. Okay, we'll talk about that more later. How am I doing on time? I go to 55, is that right? 50. I should really look this up before I get here. I did, I just forgot. Where am I? Oh, here I am. Okay, so Herschel and his sister and his son all got together. So the same guy who made this map, that isn't quite right, but is a great start, made a catalog of nebula. What's a nebula?
Isn't it like a birthplace for stars?
Now it is, but when he was writing, it was kind of anything that's up in the sky that's not a star or a planet. It's like anything that's fluffy.
Anything that looks like a cluster or a cloud?
Yeah, anything that looks cloudy. Anything that's got some distributed shape to it that's not just a point of light. So back in the day, that was anything fluffy. So there are nebula that are the birthplaces of stars, and we usually refer to those as nebula now. But they also refer to galaxies as nebula. That was, and there are more galaxies that you can see than there are star-forming regions. So he called them nebula. He made this catalog of nebula, which is just fluffy things, but it's mostly galaxies. Had about 5,000 galaxies, and then they made another one And they discovered this thing called the planetary nebula, which has absolutely nothing to do with planets, but they called it that. Here's a thing in astronomy, because it's an old field, people have been doing astronomy for a long time. We're stuck with a lot of the terminology baggage. So there's some terminology baggage that I'm going to complain about, mostly because I like to complain, but also because it's important to talk about the inconsistency. So a planetary nebula has nothing to do with planets. It's the death of a star. I'll show you some of those in a second. Oh, no, I'm not. They're pretty cool, but we're not going to talk about planetary nebula at all in this class. I might show you some pictures. William Parsons built this thing. They called it the Behemoth, I think. Look, these are stairs. This is a huge telescope with this really long barrel that can magnify like crazy. He did these magnificent sketches. I know, it's great, isn't it? Somebody, I forgot to write it down, but somebody sorted out what this guy is. I forget who that is, but it's the Smiley Face Nebula. And this is his drawing of M51, which is one of my favorite galaxies for a lot of reasons. Mostly it's splat face on and you can see all the magnetic fields in it. I'm not going to talk too much about magnetic fields in galaxies in this class, but it's a thing that I like. So M51 is this galaxy here, and it looks just like this. His drawing is so great. So Parsons, but all he was doing was like taking drawings of these things. Like he drew this thing, this splotch of stuff, but he had no idea what it was. It's just some fluffy blob of light. And maybe it's a fly on the lens of the camera, or maybe it's something enormous. Okay, John Dreyer. So, did I say out loud? They called this catalog the New General Catalog, or the General Catalog of Nebulae and Clusters. John Dreyer came along and made the New General Catalog. And let's see, he died in 1926. He made this in like 1888. He made this New General Catalog. We still use this catalog to describe galaxies. So the NGC numbers. When you see a galaxy, there are a bunch of different catalogs. Galaxies have a bunch of different names. So there's a bunch that are NGC and then some number. And that stands for the New General Catalog, and then the entry that it is in that catalog. This catalog is like 150 years old. No. Yeah, like 150 years old, but we're still using it. And then he made the index catalog, which had another in 1908. So now, again, more than 100 years old. But we're still using it because the objects haven't like gone away. So, yeah.
This is a silly question, but like why? So I just realized that NGC stands for New General Catalog,
Yeah.
and I see that a lot of things in space have like an M in front of them. What's the
Oh,
M
yeah.
for?
So, like, M51,
Yeah.
M is for the Messier catalog.
Oh, okay.
So that's this catalog here. So the Charles Messier catalog, there's like 100 and something, like 105 objects in this catalog. So M1 through 105
Messier
is the
Makes
Messier.
sense.
Yeah. Which is exactly why I put this up, is that question there. So why do we call these things? Is because of what these old people did. So thank you. So now, okay, we have all these nebula. What are these objects? I can tell you what they are. This is galaxy. This is a star-forming region. This is a galaxy. Why can I tell you that? Because I've been studying this, and I have the advantage of Hubble and Alan Sandage and all of the greats that have come before me that have described what these objects are. But until you know how far away this is, that's really the key. How far away is that? If I'm wrong in my distance by a factor of 2, then I'm wrong in the mass by a factor of 10, right? Because if it's twice as far away as I think it was, then it's twice cubed as massive. So 8, not 10, but if you're wrong in the distance, you totally can't explain what the object is, leading up to all of the time we're going to spend on the distance ladder. So what are these objects? In 1922, they call it the Great Debate. Kapchin did a lot of work on proper motion, so that's motions of the star in the plane of the Milky Way. So he looked at what those galaxies are, and spectra, and made a 3D map of stars in space. And he said that the galaxy is an oblate spheroid, so that means it's like a blob. That's 8,000 parsecs long, and the sun is about 600 parsecs from the center. That's not right. This is puts us right in the middle, which we already had problems with Kepler putting us right in the middle and pissing off the church. So this is uncomfortably heliocentric. See, he didn't understand the dust. He said it was Rayleigh scattering and wasn't important, so he got the dust wrong. But dust is actually super important, so that's a problem. So caption was one side. Harlow Shapley, he looked at the globular clusters around the galaxy. So our galaxy has these globular clusters that I never thought that I understood, and now that JWST has some images of some very, very early globular clusters, now I really don't understand. So he looked at the globular cluster distribution, and I'll talk about what that means later, but there's these clusters that are around the galaxy, and you can measure what those things are doing, and he said that the center of the galaxy is centered on Sagittarius. That's right. And the sun is about 15 kiloparsecs from the center. That's way different from this other picture, which had the whole thing is only 8,000 parsecs long. And now we're 15 kiloparsecs from the center, which is closer to right. And the galaxy is 100 kiloparsecs across, which is not bad. So we have these two pictures, both of which have aspects that are correct. One says that we live in a little galaxy, so that external nebula, M51, that would be an external galaxy. In this galaxy, M51 might be part of the galaxy because this galaxy is huge. Right? We don't know where, remember, we don't know where M51 is. It might be in the galaxy that we live in. And if it is, then it's like a blob of star-forming crap. Hard to say. So there was a great debate. They went through details. It's interesting to look at all of the details, but of their arguments. So Harlow Shapley was for a large Milky Way, and spiral nebula are small inside the galaxy. That one's good. This part's not good. Herbert Curtis on the caption side had a small Milky Way, not right. Spiral galaxies are outside of us. That is right. So neither of these guys were right. It wasn't until this woman came along and actually could sort everybody out. This is Henrietta Leavitt, who was a computer in the early 1900s. The Harvard Center for Astrophysics had teams of women to do math that just did math like crazy monsters and like really could calculate like crazy. And she was one of them. And one of the things that she discovered was this period luminosity relationship, which hopefully heard about when you took intro. What does that tell us? So this expression, F equals, I wish it had a name. L over 4 pi d squared. So the inverse square law, this is great if I know what L is, but I don't. Pretty much ever. So if I know what L is, F is what I measure with my telescope. I have a hand on that. That's the thing that I just measure. I go measure that. L, I gotta figure out what that is. And once I know what that is, then I can measure D. That way I can get D from what L is, but I need to know what L is, and that's what Leavitt did. So what Leavitt said was that there's a relationship between the period of pulsation of this kind of star, and I'll talk about what that is in a minute, probably not today. There's a period of pulsation. So these stars are kind of awesome because they're kind of like a gasoline engine. Do you guys know how a gas engine works? Like a 4-stroke cycle. So that's all right. So there's dust in the atmosphere of these stars. They're called variable stars. And as the star contracts, the density goes up and the star gets more opaque. As it gets more opaque, the heat can't leave, so it gets hotter. What happens when it gets hotter? It expands. And when it expands, the opacity goes down and it can cool, which means it can contract, which means it will get hot, which means it will expand. So they have this really nicely calibrated, really nicely described cycle of expansion and contraction, which means that they get brighter and dimmer on this very regular period. And it's proportional to how big the star is in the first place. Bigger stars do it slower because it's bigger. It takes a longer time for the whole thing to relax. More than just it's bigger, but it's bigger. So it takes longer. So she found this magnificent relationship between the period of the pulsation. That's a thing I can measure just by looking at a thing, and I got a clock. I just measure the clock. These usually take days, so I got a calendar. So you measure its brightness every day for a couple of weeks, and you get the period of the luminosity. Then I know what the luminosity is, and then I know what the distance is, and that's pretty key. So she made this super important discovery. She was gonna be nominated for the Nobel Prize, which would have been the first woman Nobel Prize and the first Nobel Prize in astronomy, but she had to die, and that's a bummer. They don't give the Nobel Prize out after you died. So I count it as a win for women in astronomy. But so then what do? Now we can measure distances. Now we can know how far away the thing is. So this is at Hubble. Let's see. So this was the largest telescope in the world. This is the Mount Wilson 100-inch telescope. Could resolve Cepheid variables in M31. It was big enough that you could see the variable stars. Let's see. Oh, do I have a picture of the? I have the picture. Anyway, it's a really satisfying plate because you can find the plate that he took, and it's this beautiful image of beautiful photograph of Andromeda, and it just says VAR exclamation point and with a circle around one of the stars, which is his discovery of what the universe looks like. It's one of the most important stars. This ends the great debate because now we know how far away things are. So now we know we've got these two pictures. Neither of them are right. Both of them have aspects that are right, but neither of them are quite right. Things are huge and far away. So this was I should have that up here. 1923, I guess. So his first major discovery was the universe is really damn big. In the early 20s, Lindblad and Oort were names that you might hear again. Started measuring the motion of the galaxy. And what they found, this is about the same time, they found that the flattening depends on rotation. And they found a lot of things about the structure of the galaxy. How they did that was using the work of this guy. This is Carl Jansky. He wrote 2 astronomy papers and has everything named after him because he did it all first. So this is the first radio telescope. So he invented radio astronomy. He was working at Bell Labs, which is the telephone company. Bell Labs wanted to know how can we use radio to put the telephone on the radio instead of wire. So now, we're totally spoiled with all this wireless technology, right? Back in the day, everything had to be connected by physical wires until they figured out how to use radio for phones and stuff. So they said, let's go figure out what the noise is. So go measure all the radio noise, all the noise in the radio bands, and tell us about it. So what parts of the universe, what parts of the planet are making radio noise? You have to understand the noise if you're going to build a communication system that's going to work around the noise. So he found that most of the radio noise comes from storms, but there's one spot. So he has this radio telescope. Let's talk about this radio telescope real quick. So this is a bunch of big loops of wire. So there are like 8 big loops of wire, and that's an antenna, and it measures radio waves as they go by. If you point the antenna like that, you can't see the radio waves. So you can rotate. So it's on tracks. You could rotate this telescope, and the planet moves. So the planet moves the telescope across the sky. So he had a pretty good coverage of what the sky was doing, and he's found one radio source in Sagittarius remember earlier, one of those pictures had the galaxy centered on Sagittarius. He found this other radio source, this really bright radio source in the middle of Sagittarius that he couldn't explain. It's always there, really bright. We now know this is the first actual measurement of a black hole, because that black hole is one of the brightest radio sources in the sky. He also developed something called the 21 centimeter line that I'm going to talk about a lot. Let's talk real quick. I'm trying to not get too deep into physics weeds today because I know everybody's brain's just getting started. So the 21 centimeter line is really important, and I'm going to talk about it a bunch because of its importance. Let's talk about what it is real quick right now. So if I have neutral hydrogen, which is what most of the universe is made of, so I have lots of it. Neutral hydrogen is a proton and an electron. And the energy is based on the energy of the electron in its orbital. So not really the distance, but based on the orbital configuration of the electron, that determines the energy of that atom. Now, in the ground state, where the electron is as relaxed as it can be, that's the coldest hydrogen. So it's neutral, unexcited, boring-ass hydrogen, which is great because it tells us what all this stuff is doing. There's a very small difference between the proton. So the protons and the electrons both have magnetic moments, and they interact with each other. Not a lot, but they do a little bit. So when the electron and the proton have spins that are in opposite directions, it's a slightly lower energy than if they're in the same direction. And if I change that direction, I have to either add or remove energy from that hydrogen atom. So when the spin flips from up to down, it gives off a very low energy photon. Remember, very low energy, E equals some number, no, just H. E equals H nu equals H times C over the wavelength. So the energy of a photon is some number times the frequency of the photon. I don't care about that number. The energy of a photon is the frequency of the photon. Everything else is units. Or 1 over the wavelength of the photon. So lower energy photons have longer wavelengths. How big is 21 centimeters? Somebody hold up their hands about how big you think 21 centimeters is. About like, yay. That is a very low energy photon. Most of the photons are nanometer sized. I can't do that with my hands. Like physically I can't. Like it doesn't matter how hard I push, they will never be a nanometer apart. And if they were, then my hands would fuse and that would be bad. I don't want that. Okay, 21 centimeter line. Low energy, so the neutral hydrogen, cold, boring hydrogen, has this low energy transition. It's not the excitation that you learn about in modern or whatever. It's this very low energy photon. Being low energy gets us two things. One, we can see with radio telescopes. Two, it goes past all the stuff. So if I've got a dust grain that's 100 angstroms across, or 100 microns across, that's pretty small. My radio wave is this big. It goes right past it. It doesn't care. So radio waves go right through the dust. Let us give, the other thing they do, the other thing it gets us is it's a line. So you know how when you're driving in your car and an ambulance goes past and goes wee 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 from the, what is that physics called? Doppler shift. I would do the same thing with a photon. So if this is what my flux looks like as a function of wavelength, so this is the first spectra that we'll put up. It's the dumbest spectra. This is all of the flux is coming out of one point, and that point is not moving relative to me. Then I'll just see this delta function. I'll just have a spike at a rest wavelength of 21 centimeters. So this is 21 centimeters plus what I measured the photon at. Now if the thing is moving, how far down this? Oh man, where's the, anyway. So if the thing is moving, we have a Doppler shift, delta F, that's proportional to the velocity, delta V over C times F. So this is just the fractional change in frequency is the fractional change in velocity relative to the speed of light. So I can use that to measure how the stuff is moving. So this is another spectrum. This is the second spectrum. So here I've got one cloud that's emitting hydrogen. It's not a spike anymore. Now it's width. It's got a width because, say I've got a cloud of gas that's neutral hydrogen and it's emitting this 21 centimeter line. Some of that gas is moving towards me and away from me because of the thermal processes. I've got these hydrogen atoms are rattling around from the thermal processes. That makes the line broader because some things are coming at me and some things are coming away from me. So I'll have some photons that are Doppler shifted to longer wavelengths and some photons that are Doppler shifted to shorter wavelengths, just from the thermal motions of the galaxy. Now, if that cloud is also moving away from me at many kilometers a second, then this line will just shift completely to a different spot. So this is a line, so here is a cloud of gas that's neutral hydrogen, that's not moving relative to me, and it has some temperature. Here's one that's got some bulk velocity in some units. It's moved, and it has some temperature. Does that make sense? Did I lose anybody on that? Yeah.
Could you go over again how what the relevance is of the 21 centimeter line to the radio waves, how that works?
Yeah, it is a radio wave. So the 21 centimeter line is a radio wave, and that's what we pick up with this big telescope. So this guy measures 21 centimeter line. So that's his job. And then we get this. And this is one of the greatest things. Looks like a splat. It looks like you poured milk on the floor. But it's a picture of the three-dimensional structure of the galaxy. This is one of the first 3D images of the galaxy that we have. How does this work? I'll go through this in detail later, so if you don't fully follow this right now, when we get to motion in the galaxy, it'll make more sense. But what we see here is a picture of the galaxy. So they point the telescope at different points in the sky, and they can make a map of what the galaxy looks like. And because we know the galaxy is rotating differentially, I know that if a cloud has a certain velocity, I have a good idea of where it is in the galaxy because I know the galaxy rotation. Or I can sort that out. If I don't know the galaxy rotation, I can measure the velocities that I get and get the rotation from that. So you don't need to worry too much. We'll come back to this graph in a couple of days. But the basic idea is 21 centimeter line is a radio line, so it goes through everything, so you can see through the dust in the galaxy. Remember that big stripe? You can see right through it, so you can see all of the structure of the galaxy. Now, this bit here is the galactic center, and it's so thick that you can't even see through it in the radio. So that's why we can't see this. But this is an image of, so this is us here, and it's an image of the distribution of hydrogen in our galaxy kind of throughout the galaxy. So that was a really important breakthrough. I guess this was 1958, so I might have jumped around a little bit. Okay, so we can measure the rotation of the galaxy. Key. We can measure how fast our galaxy is rotating, and that's related to what's in it. Okay, Zwicky, this is Fritz Zwicky, who used the virial theorem to measure the velocity of the galaxies in the Coma cluster. And he found that they were way too damn high by orders of magnitude. So what he did was he said, okay, I'm going to measure all the light that I see and say that's the mass, and I know F equals ma, I know Kepler's laws, I know how fast these things should be going around, and they're not going around that speed, they're going way, way, way faster. This 1933 measurement is the first actual measurement of dark matter, but he didn't call it that. He suggested that it was viscosity, which doesn't make any sense actually, but that's what he had, because he certainly wasn't going to posit a whole field of missing crap just for one bad measurement. So this is the Coma cluster. This is his image of it. And then in the 70s, Vera Rubin started to really carefully look at galaxies. This is a cluster of galaxies, but she started to look at galaxies themselves and the kinematics of galaxies and said every galaxy is just rotating too damn fast. They're all spinning really fast. They shouldn't be doing that. What the hell? I don't remember who first posited dark matter. I don't think it was Rubin. But she certainly made its necessity very clear. This guy wrote this.
General relativity?
Yeah, this is the field equation. And what this says is that curvature equals energy. So if space curves, it has energy. Everything has to balance. So this G here is the curvature. This T is the energy. These are constants. This lambda, we all hate a lot. He stuck this lambda here because what Newton found a long time ago was that a universe with gravity is going to collapse on itself. Einstein hated that, so he added this thing to keep the universe supported. Turns out we need to add this thing to make the universe blow up even harder than we thought it was doing before. So this lambda is one of the biggest problems in physics, I think. One of the biggest problems to human knowledge is, what is this lambda? We know it's there and we know it's huge, but we know basically nothing about it. We weren't there yet here. So when he was alive, he just put this in to try to make everything hold still and not blow up. So that's all right. Friedman and Lemaitre, we'll talk about the Friedman and Lemaitre equations. And they have, this equation has black holes and it has the expansion of the universe in it. It's this guy here is a very rich equation. Okay, I kind of went out of order a little bit. 1929, Hubble used his new distance stunt and measured the distance and the Doppler shift to a bunch of stuff and said, if it's further away, it's moving faster. And then he thought for a minute and thought, well, that is what expansion looks like. If it's expanding everywhere, everything's moving away from me. That's weird. He also found this very nice linear relationship, and this is another one of the most important things that we'll talk about. V equals h naught times d. H naught is a number, about 70. Maybe it's 68. Maybe it's 72. Now it's time to have a fight about what this number is, because depending on how you measure it, you get different answers. This is a horrible open problem in physics because we're not sure what to do about it. And I'll talk about that more. But before that, okay, so let's think we are now 6 or 7 years ago before we really had a problem with what h naught was. There's this number that relates velocity to distance. So if something is 2 kiloparsecs away from me, it is moving at h naught times 2 kiloparsecs. No. 2 kiloparsecs is still in the galaxy, not expanding. 2 megaparsecs. If something is 2 million light years away from me, then its velocity is 70 kilometers per second per megaparsec times whatever I said, 2 million. That gives me the velocity. It gives us a really great way to measure distances, because when things are moving near the speed of light because of the expansion of the universe, I know that all the velocity that I see is just from this expansion of the universe. Now, for closer things, this doesn't work, but we'll talk about that later. So Hubble in 1929 discovered that the solution to, is the universe going to collapse on itself, is that the universe is expanding. Now, this was the foot of a debate that's been really raged until the mid-90s. By the end of the 90s, everybody was pretty on board with an expanding universe. There aren't a lot of voices now that are contrary to an expanding universe. Alpha, beta, and gamma, which is ABC. They asked beta to be on this paper just because then it was ABC, but beta made it a good paper. So anyway, these guys, and Fred Hoyle, they said, okay, if it's expanding, it's cooling. So if you go the other way, it's heating. So the universe must have been really butt-ass hot a long time ago. So hot that nuclear fusion must have been going on. So hot that we can sort out exactly how much hydrogen and helium we should have. So it was so hot that the hydrogen that we have could be forming into helium. And if you understand those dynamics, then you could say, okay, how long did this process take? We got about 25% hydrogen, or 25% helium. And it turns out that 25% of the observable universe is helium. So this is a pretty strong win for working out where the elements came from. How am I doing? Oh, I only got 2 minutes left. Oh, I gotta talk fast. So I've only gotten to the interesting stuff. That's all right, we've got plenty of time. This is Penzias and Wilson. They were, again, working for Bell Labs. Again, trying to figure out what the noise was. Now they were trying to do it with shorter wavelength photons. So these are centimeter wave photons, not quite the big radio photons. These are littler microwave photons. So these are a few millimeters to a few centimeters. And what they found was a bunch of stuff about noise, so that Bell Labs could successfully use centimeter wave carriers for their communications. But they also found this extra 3 Kelvin radiation that's everywhere, completely uniform everywhere in the sky. They have this 3 Kelvin background signal. Yeah.
Is it the cosmic?
Yeah, this is the cosmic microwave background. They won the Nobel Prize for this. They didn't win the Nobel Prize for finding it. They won the Nobel Prize for finding it and explaining what it is and saying, hey, look what we found. It's the light from the Big Bang. Oh, is there another class in here? I see people lining up. What?
Nuclear astrophysics.
What's that?
Nuclear astrophysics.
Oh, what time does that start?
12.
What's that?
Well, 12:30.
12:30?
Yeah.
This is a one-time. They double booked the room.
They double. That's okay. Next week I'm moving downstairs, so it's okay.
Yeah, same with us. We're in a different building, but.
Okay. Sorry about that. Anyway.
Maybe we did the same room.
Yeah.
You're done?
No, I'm not done. Hang on one second. Okay, Kobe, CMB, very cool. WMAP, CMB, cooler. You get a Nobel Prize for this. I don't think they got a Nobel Prize for this or this. Planck, even better. These bumps tell us how big the universe is and how much dark matter's in it. It's a very cool wiggle. We'll talk about these wiggles later. And then there's supernova. I guess that's it. Yeah, there's cool stuff. I ran over all the stuff we'll spend time on. So